Welcome to this lecture. So, in the earlier lecture, I will talk about angular momenta or angular momentum. Now, in this lecture, I will talk about addition of angular momentum. So, to understand the concept of addition of angular momenta, let us take an example of addition of two angular momenta we will discuss its general formalism here. Its general formalism here. So consider, for this let us consider two angular momenta J1 and J2 which belong to different subspaces spaces 1 and 2, let us call. Is J1 and J2 may refer to two distinct particles or two different properties of same particle For example, what does it mean that two different properties of same particle? Let us try to understand this. This is clear from certain example. For example, one property refer to orbital angular momentum and other refer to spin angular momentum of same particle. Here I will split this lecture into 2 or 3 parts depending upon its length. So Now let us start discussing it. So the component of J1 and J2 and J2 satisfy usual commutation relation of angular momentum J1x comma J1y, its commutator must be equal to iota h cross J1z, and similarly J1y, J1z, its commutator is equal to iota h cross J1x, and J1z and J1x, their commutator is equal to iota h cross J1y. So let me call it as equation number 1. And similarly, for the second particle, it will follow similar commutation relations. J2x, that J2y, its commutator is equal to iota h cross J2z, and J2y comma J2z is equal to iota h cross J2x. Similarly, the last one is J2z comma J2x, its commutator is equal to iota h cross J2y, and let me call it as equation number 2. Since this J1 and J2 belongs to different spaces, therefore their components commute. Therefore components commute, that is J1j and J2k. This is for the first particle and this is for the second particle, and that will commute where both j and k may have values x, y and z, right? And let me call it as equation number 3. Now denote the joint eigenstates of J1 square and J1z by J1m1 and those of J2 square and J2z by J2 comma m2 So we can write this J1 square J1 M1, it must be equal to J1 into J1 plus 1 H cross square, it is J1 M1 and J1Z J1 M1, it must be equal to M1H cross J1 M1 and J2 square by J2 M2, it must be equal to J2 plus 1 H cross square J2 M2 and J2Z is J2 M2 is equal to M2H cross J2 M2 . Now consider two particles one and two together belonging to different subspaces Now their four operators J1 square J2 square J1Z J2Z form a complete set of commuting operators and they can be jointly diagonalized by same state. So let J1, J2, M1, M2 represent their joint eigenstate and can be written as direct product of J1 M1 and J2 M2, that is, I can say that J1 J2 M1 M2 must be equal to J1 M1 ket J1 M2 ket. Now, since these J1 and J2 are independent, therefore we can rewrite equation 4 to 7 as follows. That means we can write down it as this: J1 square J1 J2 M1 M2, it must be equal to, since it is operated with J1 square, so it will affect only J1 and M1, right? So it can be written as J1 plus 1 H cross square J1 J2 M1 M2 and J1Z J1 J2 M1 M2 must be equal to, now this J1Z, it will affect only J1 and the value of M1 because it is operated with J1Z. So that means I can write down it as M1H cross. It is J1 J2 comma M1 and M2, right? It can be written in this way. And similarly, J2 square, it can be written as this J1 J2 M1 M2 must be equal to J2 J2 plus 1 H cross square J1 J2 M1 M2, and it is J2Z J1 J2 M1 M2 must be equal to M2H cross. It is J1 J2 M1 and M2, right? Also, the ket vector, or the ket J1 J2 M1 M2 form a complete and orthonormal basis. So let us try to understand that how it forms a complete and orthonormal basis. Since we know that since J1 M1 and J2 M2 are complete and orthonormal, this means that J1 M1 is equal to 1 and it is summation over M1. Similarly, this is for its completeness condition. Now its completeness condition can be written as summation over M2. It is J2 M2 and it is J2 M2. It's equal to 1. Right, this is the completeness condition. Now another condition is that this J1 comma M1 prime, it is J1 comma M1, it is equal to delta J1 prime J1 delta M1 prime M1 and J2 prime M2 prime, and it is J2 M2, it is equal to delta J2 prime J2 and delta M2 prime M2, right? So this is the condition for orthonormality. So if I use these conditions, then I can say that this, if I use this, then I can write down it as if I take product of these two, then I can say that M1 J1 M1 J1 M1 and summation M2 J2 M2 J2 M2 and their product is equal to 1, and I can write down it as summation M1 M2 J1 M1 J1 M1 and J2 M2 and J2 M2. This is equal to 1, and this can be written as this J1 summation M1 M2, it is J1 J2 M1 M2. Similarly, it is J1 J2 M1 M2, it's equal to 1, right? So this is the completeness condition, right? Then let me talk about orthonormality condition. So orthonormality condition can be written as since I know that this J1 prime J2 prime, M1 prime, M2 prime, it is J1, J2, M1, M2, it must be equal to J1 prime, M1 prime, then J1 comma M1, and it is J2 prime, M2 prime, J2, M2, and this can be written as delta J1 prime, J1 delta for this J2 prime, J2 delta M1 prime M1 delta M2 prime M2. So this is the orthonormality condition for this, right? Let me call it as equation number, this is the equation number 13 and this is equation number 14. So let us now introduce step operator. Step operator, and it can be introduced as this J1 plus minus is equal to J1x plus minus iota J11, and J2 plus minus is equal to J2x plus minus iota J2y. Now let us now discuss the action of step operator on J1, J2, M1, M2, right? So for this, let us recall an equation. As we know that this J plus minus Jm, it can be written as H cross J minus plus M, J plus minus M plus 1 whole under the root J M plus minus 1. So therefore, using this identity, I can write down as this J plus minus J1, sorry, not J1, J1 plus minus J1 comma J2 M1 comma M2. It can be written as, now this is J1 plus minus, so that means it will act on only J1 and M1, right? So, and J2 and M2 will remain as it is. So keeping this in mind, I can express it as H cross J1 minus plus M1, and it is J1 plus minus M1 plus 1 whole under the root, and it is J1 as it is, J2 as it is, and now I can write down this M will be changed, so it is M1 plus minus 1 comma M2, because this J1 plus minus, it will affect only these two things according to this formula, right? So similarly, I can write down J2 plus minus J1, J2, comma M1, comma M2. It must be equal to, it is H cross J2 minus plus M2, it is J2 plus minus M2 plus 1 whole under the root. Now these two will change, sorry, J2 and M2 will affect, so it means J1, J2, comma M1, M2 plus minus 1. So this is a very important step which we have to keep in mind. Now, since J1, J2, M1, M2 has dimensions 2j plus 1, 2j1 plus 1 into 2j2 plus 1, right? So these are the dimensions of this, and but if I try to look at this, j is equal to, it is j1 plus j2, then their dimensions are different than this dimension. That means we cannot add two angular momenta. Add two angular momenta because of different dimensionality, right? So that means we have to do something else. So let us proceed further. Since J satisfy commutation relations of angular momentum, commutation relations of angular momentum, that is jx comma jy is equal to iota h cross jz. We have also stated it earlier in the beginning, but for different particles. So this is a general formalism. It is equal to iota h cross jx, and similarly jz comma jx is equal to iota h cross jy. Now consider j square is equal to j1 plus j2 its whole square, and it can be written as j1 plus j2 and j1 plus j2, and if I multiply these, then they can be multiplied as j1 into j1 plus j2 plus j2 into j1 plus j2. It's a simple algebra. So it is j1 j1 plus j1 j2 and j2 j1 plus j2 j2, and it can be written as j1 square plus, and both are equal, so that means it can be written as j1 and j2 plus j2 square. And let me write down it as j1 j2 square plus 2j1 and j2, and let me write down it in their components. So if I write down it in terms of their components, then it can be written as j1 square plus j2 square plus 2j1x plus j1y j1z. This is the value of this, and the value of this will be this j2x plus j2y and j2z. So it's simply a dot product, so it is this into this, and rest of the components will be 0. It's like a dot product, as a dot p can be written as ax bx plus ay by plus az bz. So keeping this in mind, I can write down it as it is j1 square j2 square plus 2j1x j2x plus j1y j2y j1z and j2z. And let me write down these separately and this part separately. So if I do this, then I can write down it as this is j1 square plus j2 square plus 2j1x j2x plus j1y j2y plus 2j1z and j2z. But now our purpose is to express these in terms of j1 j2, or in other words, I can say that we will try to express this in terms of ladder operator. So to do this, I am writing down it as directly that this part is equal to, this is equal to j1 plus j2 minus plus j1 minus j2 plus, right? I am writing it as directly, right? So this is the value of j square, and this is a very important formula. Now after this I will proceed in the next lecture, but in this lecture I will try to prove that how this part is equal to this one. So to prove this, let us proceed as follows. So that means now my purpose is to prove this part, and this is the last part of this lecture, that is, prove that this 2j1x j2x plus j1y j2y equal to j1 plus j2 minus plus j1 minus j2 plus. That's what I want to prove. So let us try to prove it. As I know that this jx is equal to 1 by 2 j plus plus j minus, and jy is equal to 1 over 2 iota j plus minus j minus. So using this, I can write down that j1x as equal to 1 by 2 j1 plus j1 minus, and j2x is equal to 1 by 2 j2 plus j2 minus, and similarly I can write down it as j1y is equal to 1 by 2 iota j1 plus minus j1 minus j2y is equal to 1 by 2 iota j2 plus minus j2 minus. So now I can write down j1x j2x as equal to 1 by 2 j1 plus j1 minus 1 by 2 j2 plus j2 minus. That means it's equal to 1 by 4 j1 plus j2 plus j1 minus j2 minus plus j1 minus j2 plus j1 minus j2 minus. And similarly I can write down the value for j1y, and j2y is equal to 1 by 2 iota j1 plus minus j1 minus. Sorry, I missed to write down the hat over this because all are operators. So right, this is this, and 1 by 2 iota j2 plus minus j2 minus. This is minus 1 upon 4. It is j1 plus j2 plus minus j1 plus j2 minus j1 minus j2 plus j1 minus and j2 minus. So if I put these values and try to find out this 2j1x j2x plus j1y and j2y is equal to 2 into 1 by 4, and this is j1 plus j2 plus and j1 plus and j2 minus plus j1 minus j2 plus and plus j1 minus j2 plus j2 minus and minus j1 plus j2 plus j1 plus and j2 minus, and it is plus j1 minus j2 plus minus j1 minus j2 minus. So if I put these here, then this term will cancel with this term, and similarly this term 1 minus 2 minus, it will cancel out with it, and this term and these this is one term 1 2 minus, these two terms are added together, and similarly this term is added with this term, so that means this is simply j1 plus, sorry, it is j1 plus j2 minus plus j1 minus and j2 plus, so hence proved. So thanks for watching this lecture, and in the another lecture I will proceed with I will continue after this.